Hi, this is a follow-up of my class notes regarding question number 5 and question number 6. So here we go. This is question number 5. And in question number 5, we have to implement my string and compare. Basically, how should I put it? This is a remake of a classic C library function, which compares up to n characters. But as far as we are concerned, we just have to make sure that we implement it, this way to follow the C code. And as long as it follows the C code, it should, as long as functionally they are the same, we should be fine. So what I'll do is I will copy the C code into the assembly file. This is from line 6 to here. And then I go to the assembly code file and paste that code in from line 4 to here. If you worry about the pound sign and combining that with if, there are two things you can do to fix that problem. One is to not to start with a pound on the first character of a line. That will make the preprocessor not recognize that line as a line to be processed. Or you can also use double pound, which also tells the preprocessor to ignore that line. So either way would work to comment out the C code properly without the preprocessor thinking about how to process that line. So now we have this code pasted in. The first thing we have to do is to handle all the parameters and displacements into the stack. So we'll start with ODBP being 0. Return address is old EBP plus 4. And as I have said multiple times, you can define a template file and bring it with you to the exam, so you don't have to enter all this redundant stuff every single time. And then we can move on to the parameters. str1 is the first one. str2 is the second one. And then we have n as the third one. Oops. Okay, double check, make sure that str1 is return address plus 4, str2 is str1 plus 4, and is str2 plus 4. So got to make sure the displacements to the parameters are all correct. When that is done, we'll go ahead and put in the actual instructions for the beginning of a subroutine, as well as the closing of the subroutine. And this is so boilerplate. You can also just create a template so that every time you start writing a subroutine, you automatically include these 4 lines of code into your subroutine. Alright, so now that that's done, we can go into the actual code over here. This is a while loop, so just because of the structure of a while loop, well, we know that we need a begin while, and we also need an end while at the very end here, and the end is actually down here. So we have end while being here. We also know that before we go to end while, we need to jump unconditionally back to begin while, just like that. So I'm just taking care of the structure of the while loop first, and I'm doing it both for the beginning and also at the end, so I don't forget to handle the end. Okay, now that we have the basic structure of the while loop, we can go ahead and actually deal with the content. So over here, let me just point out, we have 3 conditions. They are all connected by conjunctions. The first one is n. N has to be non-zero. The second one is whatever str1 points to has to be the same as whatever str2 points to. And then the third condition is whatever str1 points to has to be non-zero as well. The most important part about this is to read the type, because str1 is a pointer to const char, and a char is a byte, and same thing applies to str2. And that's going to be the most important part, is to observe the width of the operand, because if you use the wrong width of operand, the program may not work correctly anymore. Okay, so I'm just going to preserve the meaning of this code here. The first thing I would do is to compare long 0 with n, because n in this case is a 32-bit integer, unsigned integer. Whether it is unsigned or not is not even important, because I just have to make sure that it is non-zero to get into the loop. Or I should say, if it is 0, we go to the end of the loop. Okay, so if I pass through here, that means n is non-zero. Then it is time to compare whatever str2 points to whatever str1 points to. Now that can be done not so quick and easily, because it has to do with we need dereferencing in this case. So there are several ways to do it. One way to do it, either way, no matter what you do, you still have to move str1 EBP into a register. We'll just pick EAX because we know that EAX can be destroyed without having to save and restore that. Excuse me. And over here, I'll just push whatever EAX points to onto the stack. Now this seems to be wrong, because we know that we only care about one single byte and not 4 bytes of where EAX points to. But that's okay, because we can always just focus on one single byte when we actually perform the compare. So we can push all 4 bytes at the same time, but we can compare just 1 byte at a time. Then once this is pushed on the stack, then we can go ahead and move str2 into EBP. Excuse me, we can move str2 EBP into EAX in this case, and we'll move byte in this case, whatever EAX points to, into, let's say, let me think. I think AL should be fine. There's nothing against using EAX as the first operand or indirect operand, and then use AL as the second operand. This will work just fine. So now we have AL being the byte that str2 is pointing to, and the byte that str1 is pointing to is on the stack. So that means I just have to do a compare byte in this case of whatever the stack point is pointing to, because that's what I just pushed. Whatever str1 points to is pushed on the stack using this line over here, and so I'm just comparing that byte with AL, which is the byte that the byte that str2 is pointing at. And if they are not the same, then we branch to the end of the while loop. Okay, and now we only have one more thing to do, is to see if str1 is pointing to something that is non-null. Now remember, we still have that 1 byte here to push on the stack, so this is a perfect time to pop that into EAX, and then we can do a compare byte. Now remember, this compare byte, not compare long. 0 with AL, and if it is 0 in this case, if it does equal to 0, we also want to go to end while. So that takes care of the condition of the conditional statement, and now we are inside the loop. This is a pre-decrement operation, which means we have the decrement first and then we compare. That's really easy to do in assembly, because in assembly, when you decrement, it automatically checks whether the number becomes 0 or not. So we just have to do a subtract long $1 from n EBP, because n is a parameter that is on the stack, and we can immediately, we don't even have to compare to 0, and we can immediately say if n is 0 after the decrement, then we can branch around the loop. I mean the conditional statement, excuse me. So we'll go to end if n is 0, and I would immediately define end if as a label over here, just so that I don't forget to do it. And now we have increment str1, and incrementing str1 really is just incrementing str1. It is add L $1 to str1 base, using EBP as a base register, and obviously the next line is going to be the same thing, except we do it to str2. Okay, so that takes care of the loop and also the conditional statement inside the loop. The only remaining portion here is the return statement. As I talked about this in the class, this is basically just an if then else statement. So we first have to compare what str1 points to str2. If it is less than, we return -1. If it equals, we return a 0. If it is greater than, we return a 1. This one is actually a whole lot easier to do in assembly than it is in C. So let's see, let me show you why I said that. Over here, I could have done something earlier to save, whatever str1 points to and whatever str2 points to, but I'm not going to do that. So what I'll do is I'll just, copy those bytes over here again. Excuse me, I will copy whatever str1 and str points to into registers, so that we'll be ready for the comparison. And that's really about the same as what we did earlier. In other words, let's show the line numbers. In other words, we have to do about the same thing as over here. We take whatever str1 points to, push it onto the stack, move str2 into EAX, move whatever EAX points to into AL, and then just compare whatever the stack points to AL. So, we'll just go ahead and copy these lines so we can use exactly the same instructions later. This is from line 17 to line 21. So we'll copy 17 to 21 over here. 17 to 21, copy to here. And I'll adjust. Indentation should be 1 less than before, because this is... Now the most important part here is the direction of the compare. In this case, we are subtracting str1, or whatever str1 points to, from whatever str2 points to, and I don't think that's the right order of comparing, so we might need to change this to AL over here, like that. And once we do the compare, we can actually pop that. We can add. Oh no, we cannot do that. Can we? Let's see. We can do the. We can do that later. All right. So this is going to do is it will. Okay, so what we'll do is we'll differentiate between the few cases. Let's start with a J and Z. Okay, we'll do a J and Z to not equal. Okay, so that means, okay, and I'll put not equal here. If it is not equal, we have to differentiate between is it less than or greater than. So we'll deal with that later. If I end up here, that means whatever the stack pointer points to is the same as whatever AL is. That basically means whatever str2 points to is the same as whatever str1 points to. In that case, we have to move a 0 into EAX, and then unconditionally branch to ready to return. And we'll go ahead and put that over here. Ready to return goes here. And one thing that we have to do, well, we don't have to do, but it would be nice to balance the stack at this point. So I'm just adding 4 to ESP because I did push EAX on the stack a little bit earlier. And here we can, well, there are 2 ways to do this. I'm just thinking about which way is better. This push here can be balanced by a pop into EAX as soon as the compare instruction is done, because that's as long as I need AL to be whatever EAX points to. So I can actually balance the stack at this point. Pop does not change any of the flag, any of the Z flag, the C flag, the N flag, and so on. So it doesn't So it's okay to put it here, after the compare and before the conditional branch instruction. Okay, now we are back to the not equal. The next one is a little bit tricky because now it depends on whether chars are signed or not. For most cases, it really doesn't matter whether it is signed or not, but chars are actually signed. That's why it is important to use a JL or JG instruction here. Which one we use, it doesn't really matter. Okay, it does not really matter because now we know that they are not equal. So we can just say, JL to less than. Okay, we'll put the label less than here. So that means if I'm here on line 52, it is greater than. If it is greater than, we can move 1 into EAX and then unconditionally branch to ready to return. So here is a good chance to double check to see if the direction of comparison is correct. So here we have jump to less than if and only if whatever ESP points to, whatever STR1 points to, is less than AL, which is whatever STR2 points to. And that makes sense. Okay? It's because if that is the case, we want to branch around to less than. In less than, we only have to move -1 into EAX, and then we can just let it fall through to ready to return. There's nothing to do at ready to return here. We just go ahead and restore the stack pointer first, and then we pop the frame pointer and then do a return. So I think this should do it. We'll double check. Okay, and we'll also make sure that we use the C version first. We'll check the C versions to see whether that runs correctly. Okay. So we are comparing only 3 characters. ABC and ABC are the same. That's why there's an equal. There's a 0 here. We are comparing up to 5 characters in the second one. But the difference shows at the 4th character, because the first string has a no terminator, whereas the second string has the lowercase letter d. And that's why it returns a -1 value. In the third case, we are comparing only 3 characters, ABC versus ABCD. But since we are only comparing the first 3 characters, by the time the third character is compared, the order cannot be determined, and therefore it returns a 0. The last one is ABC versus A, and we want to compare up to 3 characters. But after we compare the second character, which is a B in the first string and a no terminator for the second one, we determine the first string is greater than the second string, and therefore it returns a 1. So now here's the moment of truth. Main, which is implemented in assembly, return exactly the same values, so we're good to go. That's question number 5. Now let's deal with question number 6. Question number 6 has structures and stuff like that, so it's a little bit more bothersome. And it's not really that big of a deal. You just have to copy and paste code, or have your own template ready to go for this kind of thing. So we'll go ahead and take a look at main.c first. Oops. There we go. And it looks kind of nasty because we have all this stuff here. We have the address of array I+1. We talked about this one in the class, but I never really finished the whole thing, so I'll go ahead and finish this whole thing this time. Since we have structures defined in q6.h, we'll go ahead and implement big struct.c first, so that we can print the displacement into each member of this structure into standard out. So we have big struct.c and pound include q6.h. Oops. And how come the syntax highlight? Oh, okay, that's a typo there. Syntax highlighting is good because it can tell me right away that I had a typo. So now we just have to print out the displacements into each individual member of Q6. So we can do a split and take a look at Q6.h in one and deal with the other one over here. We'll go ahead and just say big underscore buffer equals to %d, and then we have the line feed character. And here, I'm just being lazy here. I'm doing everything in without the macro. So we are casting struct big obj. So now we are casting obj points to buffer. So we are casting this whole thing. Oh, forgot about the address of that, which is redundant, but that's okay. It doesn't hurt. So we are subtracting the address of the entire structure from the address of that member, so that we can count the number of bytes in between. And once we have this, we just copy and paste it. Copy and paste is really not a very good idea. I'm doing it here just because I'm sloppy. So you should not be sloppy as me when you're doing this. But I'm just showing you that even without the macro, it's really not that big of a deal. So now we have all three defined, and we just need one last one for the size of a big structure. And we just need to use size of. Size of obj works fine. Just like that. And I think that should be it. Alright, so the first thing I want to do is just to make q6.inc, and it complains line 7, 8, and 9. Oh, right, because I don't have a pointer, I actually have a structure. I knew there has to be a value of using the macro that I have defined already. That's okay. Easy enough to fix. Okay, so the first thing we want to do is not to blindly trust q6.inc. So we want to take a look at q6.inc and also q6.h just to make sure that they make sense. Okay, so next. Oh, yes, okay. So right here we can do the comparison. Buffer being the first member should have a offset of 0 from the beginning of the structure. I is the second one, and here I is the second one. The first one has 25 characters, but it actually pads 3 more characters so that all the members are 4-byte aligned. And that's why in the assembly version you can see that I starts 28 bytes away from the beginning of the structure. The next one is 36. That's because I itself is an 8-byte integer. And then we have p next is a pointer, and that's why the size is 36 plus 4, which is 40 bytes. So they all make sense. That means you don't have to worry about q6.inc much anymore. And now it's time to actually go ahead and implement the subroutine from line 7 to here. And then we go to init big array.s, paste it in, and this time we want to go from line 3 to line 15, substitute the beginning of each line with a space first, and then 2 double pound signs, and then another space, just to make sure the preprocessor doesn't get confused and try to process anything that starts with if or else or something like that, which are completely missing in this case. But it's just a good idea to make sure that there's no chance the preprocessor can get confused. And we also need a pound include. In this case, it's q6.inc and not q6.h, because we want the assembly version, not the C version of the structure. And now we are ready to get started. Same thing. Old EBP is 0. Return address is old EBP plus 4. The function itself does not return anything. That really helps to simplify everything. Array is return address plus 4, and then n is array plus 4. So now that we have all the displacements done right, it's time to just do the boilerplate entry point code. and boilerplate exit code like so. And now we are ready to go into here and deal with the inside of this. Alright, so in the C code we have a local variable I. I'll just go ahead and implement it exactly the same way. So we'll say I is old EBP minus 4, and that's my only local variable. So that means, after I set with the frame pointer, it is time to add $i to ESP to reserve space for my local variable I. Okay, well, or I can use push $0 to initialize I at the same time, but I'm not gonna do any shortcut like that. We'll do it, really by the book, step by step. That's a move $0 to I EBP because it's a local variable. And next we have a loop. So that means, we can basically start with begin while, and at the end we have an unconditional branch to begin while, and after that we have end while. Alright, so these are the three ingredients for for any while loop. And now we can try to handle the condition. We want to compare I to n minus 1. Again, there are several ways to do it. We'll do the computation of n minus 1 first. So we'll move L and EBP to a register, let's say EAX, subtract 1 from it, and then we want to compare that. So in this case, we want to compare it against I. So we say EAX I EBP, and if it is not less than, now it is important to know what is I and what is N. N is unsigned and I is signed. And in that case, we have to pick one interpretation of the result. But because I is initialized to 0 and it only increments for each iteration, so essentially it is unsigned. There's no, it should not go negative in this case. So a unsigned conditional branch is fine. That means if I is not below n minus 1, we should exit. If I is not below n minus 1, so if I is not below, then we want to go to end while. There we go. So now we are in the loop. This is an assignment statement. First thing we want to do is to deal with the right hand side. The right hand side needs to refer to array bracket I plus 1. There are many ways to shortcut this because we know that I starts from the beginning of the array and it just increments by 1 for each iteration. And I could have just kept track of a pointer and increment the pointer by the size of each element of array for each iteration. But let's just say that we don't go for that sort of optimization, and we'll just do it by the book. We'll evaluate the right hand side, figure out what the address is, and then put it into the left hand side. So we'll just do it by the book. That means we have to move L I EBP into EAX because I know that one of the things we want to multiply has to be in EAX. So you might as well just be I plus 1. Remember to add 1 to it first before the multiplication. And now we have to specify what we want to multiply. What do we want to multiply it with? And that would be the size of each element in the array. Each element of the array is a big structure, so we just say big size here. And now we have EAX storing the result of the multiplication. We just have to add the displacement to array relative to the frame pointer. We add that to EAX, and then we have to add EBP to EAX, and now EAX is the address of the right hand side, array bracket I plus 1. I'll just push it on the stack because I know that I need that later, but I need EAX for the computation of the left hand side too. So I'll just push this one on the stack, and then we'll use EAX to compute the other side. So as I said earlier, we're not gonna do any trick. So this time we'll just redo the multiplication. This is obviously quite non-optimal, but that's okay. We'll just go ahead and do the same thing. Okay. Now we have the address of array bracket I in EAX, and we want to access the p next member of that thing. So we now have to add big underscore p next to EAX, and EAX now stores the address of the p next member of element I of array. And the magical moment to store something into it is this: pop L into whatever EAX points to, because EAX does point to the p next member of the element already. So we can just pop whatever that we pushed on the stack earlier, which is done here, and that's the right hand side, and we just pop it into whatever EAX points to. So that takes care of that. Over here, a more array indexing, and we'll just go ahead and be a little bit lazy about this. 33 to 37. Okay, so 33 to 37, copy to here. Except in this case, we don't want p next, we want member I. But nonetheless, EAX is still an address of a member of an element in the array. That's the important part. What we want to store into it is the negation of the value of I. Again, there are quite a few ways to do it. I'll just do the calculation of the right hand side before we do the calculation on the left hand side. So that means we have to do a I'm just thinking about which way is the fastest way to do it. This may be the fastest one. Put a 0 into EAX and then say subtract long. Okay, I have to remember the direction of the subtraction. We subtract the first operand from the second operand and then store the result into the second operand. So now we have to specify I EBP as the first operand and subtract that from EAX, which is already 0, and now EAX has the negation of I. And we'll just go ahead and do the same thing, push it on the stack, and when we are done computing the address of the left hand side, we'll just pop that into whatever the address points to. Okay, now we have plus I. Plus I is just adding 1 to my local variable I, like that. Alright, so now we have a few more things to do. They're both trying to access array bracket I. One is accessing member I, and the other one is accessing member p next. So in this case, I'll do maybe a little bit different. I'll compute the left hand side first. The left hand side is done by line 43 to line 47. Thereabout, close enough. Okay. Okay, this is the part that I will remove. Okay, because at this point we know that EAX points to element array bracket I. Okay. So from here, I want to reuse the same calculation because I don't want to have to go through the same calculation over and over again. We'll deal with storing negative I into that result first. And let me see. Okay, we'll go ahead and compute negative I first. So we'll still have to deal with the right hand side first because this is not something that I can do with just an immediate operand. So we might as well just do this one first. Same thing. Yeah, move a 0 into EAX. Subtract long I EBP from EAX. Push it on the stack. And now this time when I store, okay, this is a really important part. When I pop the right hand side, I don't pop it to whatever EAX points to, because EAX is pointing to the beginning of an element of array, which is a big structure. So what I need to do is to specify the displacement to that member. In this case, it is member I. So I specify big underscore I as a displacement and use EAX as a base register. This will store the right hand side to member I of the structure pointed to by EAX. And doing this is kind of nifty because in the next instruction I still have EAX pointing to the beginning of the structure, and this time I'm only storing a 0, which is easy because I can always specify an immediate operand for the 0. And this time I want to store to big underscore P next, which is the displacement from the beginning of the structure to member P next. And since EAX is still pointing to the beginning of that structure, I can continue to use that as a base register. And that should be it. That's the end of the subroutine. And we'll go ahead and see if it works. Make clean first. Make main C. This is the behavior of main C. It looks really simple, but it does test whether the subroutine is initializing the array correctly or not. So now we can say make, and of course I made a mistake somewhere with the mole instructions. Looks like I made the same mistake for all of them. So we just have to look for all the mole. Okay, it doesn't like the use of an immediate operand for the only operand type mismatch for mole. Alright, it's not a big deal, it's just a little troublesome because we just have to move L dollar big size to EDX, because EDX is going to be trashed anyway, so we can specify EDX here. So this way we are not trashing any more register than we have to. The same thing over here, move L dollar big underscore size to EDX, and then we multiply using EDX. And here's one more. I should have copied and pasted. That's okay. Typing exercise is good for you. So big size to EDX, and use that for my mole instruction. I think I fixed them. Oh, I missed one here. Alright. So we'll do it to okay. There we go. So now I think I got all of them fixed. Well, we'll have the assembler deal with that. And it's not working. Well, if it's not working, we have to. Well, I know several things. Okay, first, the numbers are unusually huge, and that's because guess what? Member I is a 64-bit number and not a 32-bit number, and we treated it as if it is just a 32-bit number, and that's why the numbers are all wrong. Okay, so that's one. The second thing is it doesn't go all the way down. I mean, I should have 10 lines of output instead of just 3 lines. Alright, so based on those two symptoms, let's go back here and fix those. The first thing we'll do is we'll fix the subtraction of I first, and all of that. Okay, that's one here. Alright, so here we have we have subtraction of I from EAX. Now, but the problem is EAX is only a 32-bit number, and what we want is a 64-bit number. There are several ways to fix this problem, and since we haven't really talked about sign extension, the only way, well, I guess in this case, the only way to fix this problem is to use subtract with borrow. Okay, now how do we do a subtract with borrow in this case? Because we have the least significant byte done here. So what is the most significant byte? I mean, what are we going to do with the most significant byte? Well, if you don't have anything here, and we know that I is going to be a positive number, so that means the negation is going to be a negative number. We also know that since I is a positive number, its own sign is going to be a 0. So that means there's no need to do any sign extension other than padding with zeros. Now that is good news, because when we do this, we can now do a subtract long, and okay, so we can do this subtract with borrow long, okay, SBBL, subtract with borrow long a 0 from, well, I guess from 0 to, but since I have nothing here, okay, we'll just go ahead and move 0 into EAX. Excuse me. Subtract with borrow long from EAX, and then we'll go ahead and push that on the stack as well. So the most significant 32 bits of the 64-bit integer is pushed last on the stack. And that means when it is time to pop it into the destination, it has to be popped first too. So we have to pop into the most significant part of the integer first, and then we pop into the least significant part of the integer. So we'll do the same thing with this part here, which is identical code. So now after the subtraction, we'll go ahead and move 0 back into EAX, and then we'll do a subtract with borrow long 0 from EAX, and oops, I forgot to do this first. So we have to push EAX first, and then we push EAX again after the subtract with borrow long, like that. Let me make sure the previous one I push it at the right place. Yep, it is. Okay, so now when we pop it, we have to do exactly the same thing. We have to pop it into big underscore I, which is the displacement from the beginning of the structure to the first byte of member I, but I this time has 8 bytes. And the first one that we pop is the most significant 32 bits of the 64-bit integer, and that's why we have to remember to add 4 to the displacement, because it is the most significant 32 bits of a 64-bit number. The second 4 bytes that we pop is the least significant part of the 64-bit number, and that's why it just goes to the base part here. That part has to do with the Intel processor. It's a 64-bit excuse me, it's a little endian processor. So we'll fix only this part, and it'll make again, and oops, it's still incorrect. Oh, okay, I might actually have to debug the program this time. And it's not crashing, it's only printing 3 numbers. The numbers have changed. You can see the numbers are not the same as before, but they are still incorrect. Alright, let's take a look. I must have done something. Okay, first of all, the loop terminated too early. It should have, well, we don't know whether the loop is terminating too early, or I did not initialize the structure correctly to cause it to exit too early. So the first thing to check is whether we actually went through the loop enough times or not. So that means we have to put a breakpoint at begin while and just count how many times we are going through begin while when the program runs. That's line 18. So we'll go for GDB init big array. Oops, nope. Should be main. Put a breakpoint in init big array.as line 18. No source file named init big array.as. Okay, run. It doesn't take that. Okay, let's make sure that when it compiles, it did not compile with a -G, so this is something that I definitely have to fix. For the final exam, this is definitely my bad, and it's a little harder for you guys to fix it. I think it's AS flags for the assembler. Give it a try. Yep, that's it. Okay, this time we can actually do the GDB correctly. Put a breakpoint at init big array.as line 18 and just run the program. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it did go through that loop 10 times. So the problem is not with the count of the loop. It has to do with the initialization that I'm doing in the loop. So now we have to go back to the assembly code here. We know the exit logic of the code is correct, and it's just a problem of not calculating the offsets of each member correctly. Essentially, p next gets a 0 too early, because it should get a 0 at the very end here, and it's not doing that. So there are two things that can go wrong. The multiplication can be wrong. So let's see here. Okay, this is I plus 1. Okay, I'll put I into EAX. Add 1 to it. I put big size into EDX. We multiply EAX and EDX. That's the number of bytes from the beginning of the array to the element that we want to access. We add array to EAX and then the EBP. So at this point, EAX should be the address of array bracket I plus 1. So I'm thinking the multiplication is the problem here. This is line 29. So let's go ahead and check that. GDB main. Put a breakpoint at, what was it again? 29? Oh. Well, let's go ahead and take a look first. 29 is the mode instruction, so that is the right place. Run the program, take a look at EAX and EDX before the multiplication. 1 and 40, that sounds right to me. Single step. Take a look at EAX and EDX again. And 40 and 0, that is correct. So the displacement is actually calculated correctly. So that part is right. The right hand side is computed correctly. Now let's take a look at the left hand side and see if the left hand side is calculated correctly. So once again, we load I into EAX, big size into EDX, perform the multiplication, add to array, which is the displacement from EBP to okay. I know what the problem is, and this is embarrassing because array is not a local variable. It's not actually an array. It is a pointer and is passed as a parameter. So that means every single time I do this, I really should have been doing that. So let me say that again. And we have to take out the other one like that. Okay, I was misunderstanding my own code. That is the double embarrassing part. I was misunderstanding my own code, and I was assuming that array was a local variable, and it is actually an array. But that is not the case. Array is a parameter, and it is a pointer to a structure, and that's why you have to add that pointer to the displacement of between the beginning of the entire array to the element that we want to access. That is why it is doing everything wrong. So every time I refer to array and add EBP to EAX, I have to get rid of this one and then change $array to a based operand. I think there's one more array down here. Yep, so we'll change this one. Okay, so let's look for arrays. 1, 2. This is good, and that's good too. Alright, and this time it works correctly. Yay! Alright, well, so that was a pretty bad confusion right there on my part, and it has to do with this part here. Okay, so once again, array is passed as a pointer to a struct big, and I was misunderstanding that as a local variable, which is actually an array. In other words, I made the mistake of misunderstanding that array is defined more like this, something along that line. Okay, this is my assumption, and that was bad because that's not what array is as a parameter. Well, this is all thanks to C does not differentiate between arrays and pointers. Okay, so it is partially my fault, but mostly it is the fault of C. Yeah, I can blame it on C. Alright, well, now that we have all both question number 5 and 6 answered, I will upload this video, and hopefully this will be of some use to you guys. I have just confirmed that we will be taking the exam in the lab from 8 p.m. to 10 p.m. on Tuesday. So I'll see you all on Tuesday.